In this video, we're going to look at how to find complex roots. Now, we're going to rely on de Moivre's theorem to help us do this. Remember, de Moivre's theorem allowed us to take a complex number and raise it to a power very easily if that number was in polar form. So, if we can raise things to powers, we can obviously take the nth root of things as well. We can undo that process, and that is why this relies on de Moivre's theorem. But just like with de Moivre's theorem, we do have to be in polar form. So let's start by defining our complex number z to be r times cosine theta plus I sine theta, the traditional polar form or the trigonometric form of a complex number. Then we can find the n distinct complex roots of z using the equation the nth root of r cosine of theta plus 2 pi k over n plus I sine theta plus 2 pi k over n. So the n is the nth root that we're looking for. What is the k doing here? We'll see this a little bit more as we work through our example, but k is representing the kth element in that sequence of roots. So if we are looking for, say, the fifth complex roots of z, that means there should be 5 roots. And the k would be telling us, are we looking at the initial root, the first, or the second? Which one of those 5 complex roots are we looking for? So that k is always going to be just a integer 0, 1, 2, 3, all the way up until n minus 1, because the 0 is counting as that first root. So that would give us n roots, 0 through n minus 1. So if we want to say the third roots, we'll be finding k is 0, 1, and 2. We have n is, say, 5. The fifth roots, we'd have 0, 1, 2, 3, and 4 for our k. So let's take a look at an example to find how this works. I should also point out in my formula, I've written 2 pi, but we could just as easily have used 360 degrees. Depends on if we're on radians or if we're looking at degrees. So if I want to find the third complex root of -8, well, let's think about this problem real quick. Let's say we had x cubed is equal to -8, and I want to solve that for x. Well, obviously, what we've done in the past is we've taken the third root of both sides, and the third root of -8, completely possible, it gives us -2. That's one of the right answers. That was the simple one that we could find from before. What we're adding to this, though, we're finding all the roots. If we're taking an x cubed is equal to, let me back up a few steps. We had an x cubed is equal to -8. We knew that there should be 3 solutions for that. The degree of the polynomial tells me how many solutions I should expect to have. So I do expect to have 3 solutions. It's just 2 of those we couldn't find before because they were complex. And so let's work to find those. Well, first thing I recognize is that -8 is in rectangular form, so I need to convert that over to polar form. And as we've done many times before, I'm going to start with a diagram. -8 purely in the real direction. Let me just stick it over here rather than drawing out all tick marks. So -8 would be sitting right here. It wouldn't be up or down at all because there is no imaginary portion there. It's still a complex number, just the imaginary portion is 0. So this one's pretty easy to look at and just know what the r value and the theta value are going to be because it's purely one-dimensional. We only have it moving along the real axis. The distance from our origin to our complex number 8, that distance there is 8 units. Remember, we have to use a positive for our r. And the angle that would get us there would be pi. Could I use 180 degrees? Sure, it would just mean up here in my formula I'll have to use 360. It does not matter. So if I were to find this complex number, it would be 8 times cosine of pi plus I sine of pi. But what we're after are the third complex roots. So I'm going to be looking for 3 things. I'll be looking for 3 roots. I'm going to call it z0. The next one will be z1, and then we'll have z2. Why am I stopping at z2 if I want to find the third roots? Well, if I look at how many z's or how many roots I have on the screen right now, it's 3. 1, 2, 3. So I have the 3 roots right there. Let's go ahead and work on this first one. So remember, the formula tells me I have to take the nth root, and because we're looking for the third root, this will be the third root of the r, which is 8, cosine. My angle was pi. I'm going to add to that 2 pi times the k. Well, the k we've defined to be 0. We're looking at the first one in that sequence. And the n still is 3. As we've said many times before, the angles always have to match. So we'll have pi plus 2 pi times 0 over 3. If I start to simplify this, the cubed root of 8 is 2. 2 pi times 0 is just 0, so I'm going to end up with cosine of pi over 3. Sine has to be the exact same thing. And because we started in rectangular form, I'm going to put these numbers back into rectangular form. If I were asked to leave in polar form, this would be my answer. But we can calculate these exactly. Cosine of pi over 3 is 1/2. And sine of pi over 3 is root 3 over 2. And so when I distribute that 2, move this down, when I distribute that 2, I'll be left with 1 plus root 3i. So there is the first of my three roots, the three third roots. Move on to z1, this being the second root. That subscript of 0, we've seen this before where it indicates the initial. So this is like our starting point. This will be our next, this is z1. So we're still going to have the cubed root of 8. That portion does not change. Let's scroll back up to the formula. The only thing that's going to change is the k. The k is becoming a 1. So we're still going to have the cubed root of 8, the same as we had it before. We have cosine. We'll have pi plus 2 pi. This time the 0 switches to a 1 over 3. Sine has to look exactly the same. Don't need that in there. So I'll have pi plus 2 pi times 1 over the 3. And so if I simplify this, we'll have our 2 out front again. That's not going to change. Our angle does change, however. We have pi plus 2 pi, that'll be 3 pi. Over 3 simplifies to just pi. Sine has to have the same angle. And so when I simplify these, put it back into rectangular form, cosine of pi is -1. Sine of pi is 0. And so we're simply left with the number -2. Remember, when we started this example, we said that -2 had to be one of the roots of -8, had to be one of the third roots. We took the cubed root of -8, that's going to be -2. So we see that in our list, we're just adding to it. And let's find the last one, the third of our roots. So I'm looking for z2. Still going to take the third root of 8, have cosine of pi plus 2 pi. This time the k changes to a 2. And sine has to look exactly the same. And when I simplify, the cubed root of 8 is 2. 2 pi times 2 here will give me 4. Add another pi, that'll give me 5 pi over 3. Plus I sine of the same. So I sine of 5 pi over 3. 5 pi over 3, we can evaluate that. It is in the fourth quadrant, so cosine will be a positive 1/2. Sine, however, will be a negative root 3 over 2. And when I distribute, I get 1 minus root 3, and I drop the I. The root 3 should have the I with it still. And so those would be our three complex roots. Let me just copy them down real quickly so we can take a look at them. All right, so I've copied all three roots down just so we can see them all in one spot very concisely. What I want to do is I want to take these and I want to sketch them out real quick. I'm going to put them onto my graph, and I'm going to just do a rough sketch because I'm not great at drawing. But 1 plus root 3, well, that would be somewhere up in here. If I were to look at the -2, obviously that's going to be somewhere over here. And then 1 plus root 3, so go over 1 and then down root 3 should be a little further down than it is left and right. So what we should see about all three of these points, especially if I was a better drawer, is they're all equidistant from each other. And I mean that in two ways. They're equidistant along their arcs, and they're also equidistant from the center, from the origin. So if I were to trace this arc going from these 2 points along the circle, let me try that one more time. So they do form a circle. We're looking at these things on a circle. So if I were to look at that arc along the circle, that arc there would be the same as this arc right here between the next 2 points. And that would be the same as this third arc right here. And again, that's a terrible circle. But the point being, if we were to put a circle on them, let me actually put a physical circle, if I can, on these 3 points. What we would see is that these arcs between them, there's a rough approximation, the arc between here and here would be the same as the arc from here to here as the same as the arc from here to here, so an imprecise circle and within precise points. All right, the other thing I'm saying is if we look at the distance from our center, get rid of the circle, we look at the distance from our center to each of these points, that line there is the same length as this line here, is the same length as this line here. All three of those lines would be the same length. And the reason for that, what we're doing is we're taking this number -8 and we're looking at the third roots of it. So what we're doing is we're taking this -8 and we're breaking it up into 3 equal parts. That's what a root does. A root takes a number and it breaks it up into that many equal parts. So we're taking -8, breaking it up into 3 equal parts. Well, we know complex numbers are spaced somewhere along the real imaginary axis. And we know that we are breaking that number up into 3 equal parts. So this distance from here to here has to be 2, this distance from here to here has to be 2, and this one here has to be 2. The angle between them is going to be the same. How can we see that those distances are all 2? Well, that's exactly what we found the moduli to be in each of the 3 cases. Each of them, when we have it in that polar form, has a moduli of 2. How can we see the angles are equally spaced? Well, what did we do? We literally took 2 pi, which is a full rotation about a circle. Full circle is 2 pi, the angle of a full circle is 2 pi. We took that 2 pi, we broke it up into 3 equal pieces. Now, we did have to account for where we started. We did add the fraction of a rotation that we were around. So if we're looking at the initial root, we had the 0 in there, the initial position. Then we plugged in our 1, then we plugged in our 2. Now, maybe you're still not convinced that I should have stopped at Z2. Maybe I should have gone on to Z3 because we had 3 zeros. Well, let's see what happens, what we get when we calculate that. We'd have the cubed root of 8, we'd have cosine, we'd have pi plus 2 pi, this time times 3, over the n is still 3. Sine, we're going to have the same. So to save space here, I'm just going to do the calculation. 2 pi times 3 is 6 pi plus another pi is 7 pi over 3. And keep in mind cosine would be the same. So we have 2 times cosine, 7 pi over 3, and sine of 7 pi over 3. And we look at that 7 pi over 3 and say, well, I need to have a coterminal angle there. I don't know how to calculate 7 pi over 3. Well, it's pi over 3. And that should sound pretty familiar because that is exactly what we started with. That was that zeroth case. And so what we found is we started at this point. That was the first of the 3 roots. We got to this one next. We got to this one next. If we're to keep going, we just keep moving our way around the circle between these 3 points because they're all equidistant from each other. They're all equidistant from the origin.